Hello and welcome to this Royal Society Publishing video podcast. Today I'm joined by Professor Timothy Leighton to discuss his paper that was published in Proceedings A that looks at whether dolphins think non-linearly. In this paper, entitled "Do Dolphins Benefit from Nonlinear Mathematics When Processing Their Sonar Returns?", the authors have developed a new method of sonar processing which may mimic that of dolphins. So Tim, what is it about dolphin sonar that first got you interested in working on this project?
About 10 years ago, I was watching a wonderful BBC Blue Planet video, which showed dolphins swimming along, trying to catch a herd of, I think they were sardines, and they were blowing bubble nets as they went. And that immediately struck me as very strange, because we know that dolphins' most spectacular sensory apparatus is their sonar. And yet we also know that no man-made sonar would have been able to detect fish in the bubble clouds that they were producing, which left a big question in my mind. Either the dolphin were doing something better than we could do with our man-made sonar, or they were blinding themselves, blinding their best sensory apparatus, their echolocation, when they were hunting. So the dolphin must have some other edge. We know that there are some edges it obviously has. It's very fast and mobile, and if it's going for a target, it can send sonar pings at it from many different directions and get many perspectives. But it also has a really big brain that's lived in the ocean for 10 million years, evolving ways of echolocating in difficult environments. So I did wonder if there was some processing going on in the brain with these sonar returns. So we looked at the signal processing that might go on if you had a lot of computing power like a brain. The students like to call this, do dolphins think non-linearly? But it's not really thinking, it's not about cognition, it's the signal processing that the brain can underdo.
Okay, so if we assume that dolphins aren't blinding their sonar, what might they be doing to process the signals in bubbly water?
Well, the first signal that I thought might work was something that we call TWIPS, twin inverted pulse sonar. And that is a sonar signal that sends out two pulses, one immediately after other. And they're identical, except that the second one is inverted with respect to the first. It's exactly the same waveform, except it's multiplied by -1. So you might call the first pulse +1 and the second pulse -1. Now both those go whizzing out into the ocean at the bubble cloud, where there's a fish and there's some bubbles. And we know both would be scattered strongly off both, particularly strongly scattered off the bubbles, and so they would clutter the image for the dolphin. A bit like fog cluttering your car headlamp. But if it uses these two pulses, +1 followed by a -1, then something very strange happens. Those pulses reflect off the fish in a way pretty much unchanged. You get a +1 and a -1 back. But when they hit the bubble and they drive the bubble hard, the bubble is a nonlinear oscillator. When a waveform, a pressure waveform hits it, that's a high pressure followed by a low, in the high pressure it can only contract. It can't contract smaller than its radius, so it disappears. Whereas in the low pressure it could expand as far as it likes. It's asymmetric when it pulsates. So a lot of its energy doesn't come back just as a mimic of the signal that hit it, but as a square of the signal that hits it. So if you like, it sends back +1 squared and -1 squared. So I thought to myself, what could the dolphin do with this? And it's an issue of, it sends out this +1 and -1 in its sonar pulses, ping ping. And when it receives the time history, it breaks them in half and adds them together. Now, if you add together the scatter from the fish, you add +1 to -1 and you get nothing. So the fish disappears from the sonar. But if you add together the scatter from the bubbles, you get 1 squared plus -1 squared, which equals 2. So the bubbles scatter very strongly and the fish become invisible from the sonar image if you send out those two pulses. But now let's take those same two halves of the echo. Instead of adding them together, you subtract them. The fish scatter +1 minus -1, which is 2. So it's a strong scatter from the fish. But the bubbles scatter 1 squared minus -1 squared, which is 0. So if you subtract the two pulses one from another, the fish scatter strongly and the bubbles become invisible. So that was great. No one would fund us to look at this. So I raised money by doing some consultancies and used that to hire a student, Dan Finfer, and my good friend and colleague Paul White. We set to work to see whether these ideas would play out. They worked in computer simulation. They worked in a big underwater test tank that we have, containing about 200 tons of water. And then finally, we dragged a sonar in the wake of some really big ships, 4,000 or 5,000 gross weight tonnage, as they steamed up and down Southampton water. So we wait for a big ship to come along, we'd steam up into its wake, and the sonar would ping and try and see the seabed through the bottom. And it worked brilliantly. So we knew TWIPs worked, and we published a paper a couple of years ago in the Proceedings of the Royal Society, and everything seems great, except there was still a question remaining, and that was, is this what dolphins do? And so I'd advertised quite broadly to the dolphin community that I was looking to the community of dolphin scientists, not the dolphins themselves, and to their community to say, look, do you ever see these pulses? And there were sort of clues, and if you take lots of different species and add the bits of what they do together, you could just about see that they had all the ingredients, but none of them seemed to be doing it, it was a half a story. We'd got a sonar that worked, but it wasn't the solution that dolphins were using.
And what is the new method that you've developed?
Well, we got TWIPs to work and it was lovely, but the question remained, what do dolphins do if they don't do TWIPs? So I got together with my friend Paul White and we hired a new student, Gimwa Chua, and we started looking at what signals dolphins do send out and whether they can make use of the same kind of nonlinear processing, the squaring of numbers and the adding and subtracting, whether they can make use of that kind of thing in a similar way to TWIPs did. Now, when dolphins send out a signal for echolocating, it sounds something like this. A series of clicks, and they can send them out really fast, so they almost sound like a buzz. So they're sending out all those signals, and but the amplitude of those signals wasn't the same. Every click wasn't the same loudness, they varied, and that was a difference. And we were interested in the differences from one click to the next. So this sounded interesting. If the variation in amplitude between two clicks could be used in nonlinear signal processing to distinguish between a fish and a bubble, it would be very exciting. So how would it work? Let's say we send out two clicks, click, and then after it, slightly quieter, click. Let's say the second click is a third the amplitude of the first. Click number 1 has amplitude 1, click number 2 has amplitude a third. So let's send them out, click, click. Now when they come back, the amplitude from the fish scatters the first pulse back as 1, the second pulse it scatters back as amplitude a third. Let's take that second pulse, multiply it by 3, and subtract it. So it's 1 minus 3 times a third gives you 0. So this time subtraction with the multiplication kills off the fish scatter, makes the fish invisible. But the bubble scatter is strong. You get 1 squared minus 3 times a third squared, which is 1 minus a third, which is 2/3. So here the bubbles, when you subtract, the bubbles are strong and the fishes become invisible. Now, let's say mentally we sent out 2 clicks, click, click, a loud and a quiet one. And this time we add them. When we add the fish scatter and multiply the amplitude of the second echo by 3, we get 1 plus 3 times a third, that's 2. So that's a strong scatter from the fish. From the bubble we get 1 squared plus 3 times 1/3 squared, which is 1 plus a third, which is 4/3. So it's not as strong as the fish scatter. So it looks like it might work. So we set about again, did a simulation, seemed to work. That gave us enough faith to set up a sonar source in our big underwater tank and do a tank experiment. we took as real, as close to a dolphin pulse as we could generate. We played it through our sonar source, did that biaps, biased pulse summation sonar, biaps processing, and sure enough, we could tell the difference between the target and the bubbles.
Is there any evidence to suggest that dolphins might actually be processing signals in this way?
None at all. All I've shown is that it's possible. If dolphins were making bubble nets and suddenly shift the frequency of their pulse down, that would be a really good indicator that it's another piece in the puzzle. It doesn't prove they're using biaps, but it would be a great indicator. If they just shift their frequency down a bit when they were making bubble clouds, so that so that whatever the center frequency of the pulse they were emitting was less than half the upper frequency limit they can hear, that would be a really exciting piece of evidence. Again, not conclusive, because it's very hard to work out what's going on in a dolphin brain, but a very exciting piece of evidence. And if they're not, it means that maybe we haven't solved the puzzle yet of what dolphins are doing when they hunt with bubble nets.
And what are the human benefits of nonlinear processing?
What we have done is, with both TWIPs and biaps, we've produced a way of generating and processing signals that can distinguish one type of scatterer from another. That's exciting in sonar, particularly as a lot of the naval operations of importance are in shallow water, where, for example, last decade in the Gulf, where there were, naval and merchant and aid vessels were very worried about mines hidden in the bubbly water. And so what we hope we do is we've developed a technology that can help in shallow water safeguard lives and equipment. But also, thinking wider, there are an awful lot of landmines that are underwater. There are improvised explosive devices. And the TWIPs and biaps processing isn't just restricted to sonar. You could use it with radar. Now, with radar, it'll tell you the difference between circuitry and soil. So you could use it to detect these sorts of devices. They discriminate between circuitry and soil in the same way that in sonar they tell the difference between a fish and a bubble cloud. So there's a lot of other exciting applications that we know potentially out there using these signals that are derived from just thinking about how on earth can dolphins use their sonar when they're hunting with bubble nets.
Thank you very much, Tim, and thank you all for watching.